Our project focuses on a Labyrinth tabletop game made by Brio, which involves moving a steel ball through a maze using the tilt controls on the side of the board. Our overall goal was to create a machine that could both, in real time, understand what's happening on the board and where the marble is going, and mechanically move the dials to compensate for what is being seen on the board. Our initial goal with this was to make it entirely autonomous. For this goal to be achieved, we had to break up our design into three major portions: the image processing, the motor controller, and the ball controller. The image processing is generally broken up into two parts. The first part involves parsing the board and finding where the holes and where the walls are. The second part involves tracking the ball and constantly updating the motor controller. To mark obstacles on the board, such as walls and holes, we initially take a capture of the board from above, and with this one image we convert it from red, green, blue to hue saturation value, and use contouring to find where the walls and holes are. After this, we then use canny edge detection to follow the guiding line from the beginning of the course to the end. With this path now laid out, we can place nodes along it, and then vectors are placed in between the nodes. This creates a path that we should generally follow to get through the maze. Now that we understand the path that we should follow, all the image processing power is now dedicated to updating where the ball is and where we should be going.
We have an AC to DC wall adapter that feeds into a dual motor H bridge, then into our 2-gear motors to power them. The direction and speed of these motors is determined by the microcontroller using PWM signals and digital output signals that are fed into the logical inputs of the H bridge to actually control them. The gear motors have optical encoders to determine the rotation of the motor shaft. The encoder signals are fed into 2 quadrature chips which increment or decrement based on the direction that the motor is turning, and the total count is then fed into the microcontroller to be used in our motor controller. The motor controller is used to turn the motor shaft to a desired angle. A desired angle signal is received from the ball controller, which is then fed into the motor's PD controller. This controller determines a PWM signal for the speed that the motor needs to turn and a digital signal for the direction that the motor needs to turn. These signals are then output to the system. The total count from the quadrature chips is then converted into a usable angle and subtracted from the desired angle signal to create the feedback loop for the motor controller.
Now we'll talk about going through the Simulink of the actual controllers and how the data used from the visual feedback was used in order to move the motors in certain ways. First, we have the block that receives the data from the visual port, and it's a 16-byte data. It's receiving 4 pieces of information. It's receiving the X and Y coordinates for the desired position and the X and Y coordinates for the actual position registered by the visual feedback. Then we have an unpack block that takes that information and makes it usable for us, and so we can demux it in the size that the data comes in. Demultiplexing means that we're splitting it up into the individual pieces of information. As you see, it goes from 1 line to 4 lines, saying that it goes from one data set to the individual 4 that I just discussed. And then we have 2 different parallel bodies in our actual code. We have the X direction and the Y direction, which develops the plane that the ball is moving in. So focusing at one direction at a time. When we developed the ball and beam, we were working at one direction at a time. So we will go through that right now in a singular direction first, working on the ball and beam. Each direction is a copy of the other, but with different values, since the board has a different length from its center axis in order to tilt the board to its maximum angle. So we have an incoming rating limiting block so that the ball cannot be expected to go from a small position value to a large position value or vice versa too quickly. And that allows us to not over torque or send information to over torque the motors past the maximum angle of tilt that the board can go to. Our summing block takes the desired position and subtracts the current position and has an error signal that follows out as the result of that block. That block is in pixels, that resulting error is in pixels. So we have to change it from pixels to meters so that the ball controller that we'll talk about in a moment will be able to use that information accurately to output the correct amount of radians that we want the board to tilt to. This next block goes into a data type block. It just changes this over. It force changes this over to a single data type, which is needed for the PID controller, which we'll talk about now. So we have two controllers within this within a singular direction. We have our ball controller, which works with the response to the ball dynamics, which is how well the ball actually moves, on the board based on the friction of the board and the angle from the fulcrum and all that. So if we go into it, we see that it's only a proportional derivative controller. There's no integration there because the ball dynamics actually come out to be a double integrator. And so we don't need an integration to we don't need an integration to offset that. That would actually make things a lot more difficult to fine tune. So we just use a proportional derivative controller. The proportional is set to 185 because we found that it becomes unstable if we put it too much higher. The derivative is set to 0.25 to kind of limit that amount of overshoot and error. Then we found that our X direction was inverse from what we were expecting. We were designing this X direction inversely from what we were expecting the camera to give us, and so we have to actually inverse the X direction after the PD controller. Now the output of the PD controller of the ball controller is in radians. So our next block, our next gain block, this K, is the board in the X direction from radians to degrees, so that we can limit that from 8 to -8, which are our maximums of the board in the X direction. Now going into the motor controller, this is an entire sub block. As I said earlier, there's two PD controllers. One that is controlling the ball and deals with the ball dynamics, response to the ball dynamics. The motor controller actually works on using a desired angle and the feedback from the quadrature counter chip that we have on our board in order to output a desired angle or a desired PWM that moves the motor to a certain position and stops it once it gets to that position. So we have a desired angle coming in on the left, top left. We have our feedback angle or our feedback quadrature count on the bottom left, and then the desired angle comes in, and it's already a degree angle, but we have to change it from degrees of turn or degrees of tilt of the board to what we want the knob angle to actually turn. in a direction, because the knob angles maximum and minimum are 45 degrees in either direction. So we force that to a single just to make sure it is. And our quadrature counter chip is just a counter, and we have this K gain that allows us to change that quadrature count into degrees, and that goes into a summing block which subtracts the two, our desired angle from our actual angle, and giving us an error signal in degrees. That goes into another PD controller, and this one is based on the actual dynamics of moving the board with the motor, or moving the knob with the motor in order to move the board to where we need it to be. And so we set this proportional gain fairly high to have high response so that the motor would move the board fairly quickly. And our derivative is fairly low. These go into to make it to the actual microcontroller.
Throughout this video, we have been displaying our machine's ability to use ball and plate mechanics and to use ball and beam mechanics both in the X and Y direction. Due to many technical difficulties, this is as far as we've gotten. But as a further demonstration, we've added videos of us tweaking the robot with the Labyrinth in play, showing generally what its movement is like and what sort of errors we are having.